Even though in our last lesson we solved everything using trigonometry, by definition that was known as the component method, as you're breaking everything down into its horizontal components and vertical components. There actually is another way of solving these problems called the trigonometric method, where you're not breaking into its components. Instead, you're using either the cosine law or the sine law in solving it. Knowing that you need to know those skill sets, here's a practice question that you can work with. Here are a few hints for you, and I'll give away the answers now. There you go. Also, just for your reference only, in case you want to jot it down, here are the corresponding angle theorems that you've learned back in grade 9 math. We're going to revisit the same exact problem. This question can be solved 3 different ways. First is through a scale diagram, but the results may be very inaccurate if you don't line up your protractor correctly. Another method is by component method, but the third method is by trigonometry, or the trigonometric method. So let's get through that. When you're solving these problems here, first thing you want to do is that you want to draw a brief sketch. It doesn't have to be to scale, but you probably want to try it as close as possible to be to scale so that your angles are meaningful. Because if you draw everything completely out of proportion, it's not going to be relevant to your final answer. Okay, so you're going to draw a brief sketch representing what's happening right now. So the dove first flies some length east 30 degrees towards the north. As for the second vector, you'll see that it's 20 meters, so it shouldn't be as long. Not that you have to draw it to scale, but you probably want to be, roughly half the original length. And you'll try as best as possible to represent north 60 degrees towards the west. I know it's not perfect here, but it doesn't have to be to scale, just approximately there so that your end triangle should make sense. Okay, so we're trying to look for that green vector. You'll see that this is a scalene triangle, and it is possible to solve this scaling triangle by using cosine law and sine law. So how about we go through solving this all real time? All right. Well, let's take a look at what we know so far. Let's just highlight it away. We have delta d1, so we know the length of this vector here. We have delta d2. We know the length of this vector over here. Lastly, interestingly enough, by using the z pattern, we can figure out the angle over here, and the complementary angle of 60 degrees is 30 degrees. So there is a way of finding out this containing angle right over here. And any time that you have a side, angle, side, you can solve this problem by using cosine law. All right, so let's get started. We need to give more context here, because if we want to use cosine law and sine law, we have to define what A, B, and C are. And just out of pure sheer habit, this always works best. If this is the vector you're looking for, call that side C. You'll see why right after. As for the other two, it doesn't really matter how you label it. I mean, if you want to go extra, like how I sometimes do, if this is the first vector, I'll call this A, and if that's the second vector, that'll be vector B. But it really doesn't matter. Okay, you don't have to worry about that. What is critical is that you label these sides. Next, let's describe angle C. Angle C is actually the sum of 30 degrees plus 60 degrees. Whoops, not 60, 30 degrees, which is equal to 60 degrees. How did I solve that? By using the Z pattern, as well as a complementary angle theorem. And that's it. That's all you need to state for that mark there. Okay, how did you get to the 60? Please show me how you got to that. Here's just the typed out version of it, nice and clean, that's all. Okay, next, as we've said from before, anytime you have a side, angle, side, you probably want to solve this by using the cosine law. And I think most of us memorize the cosine law as such. C squared is equal to A squared plus B squared minus 2AB cosine C. I wasn't even looking at the screen. All right, and I hope that you now you know why I chose this as side C. All right, because that way we can just take the formula and leave it alone. We don't need to rearrange it or anything. We could just write it out from route memory. Okay, so that's the hint. If this is the vector you're looking for, make that side C. Makes your life a whole lot easier. Did you see that? Okay, now we can sub everything in, and yes, I'm a stickler for it. Include units in your substitution. All right, I've mentioned many times before that any number without a unit is completely meaningless. So please give it some meaning. And the units will work out anyways, because you'll have meter squared plus meter squared minus meters times meters, which is meters squared. Meter squared plus meter squared gives you meter squared. Subtract meter squared, you still have meter squared. You're going to square root it, and square root of meter squared is just meters. So the units will work out. You probably want to carry more significant figures than what you started off with, at least one minimum. I always recommend two, okay? Because this number here you will have to reuse. It's the only way to get to the next stage, all right? Because what we have now is that we know this side length, we know this side length, we know this side length, and we know this corresponding angle. What we're really interested in is x marks a spot. In other words, angle B. How can we solve for that? All right. And with what we're given over here, the best way of attacking it is that any time that you have a side and a corresponding angle, you're better off just using sine law and solving it. Okay, so since we know angle C and side C, well, sine C over C is equal to sine B over B. Isolate for B, as in this B over here, by bringing the B up here and then sine inversing both sides, and you get the formula looking like this. Sub everything in, crunch through it super carefully. Units will always work out. You'll see that meters divides out with meters, and we get a ratio. Trigonometry only works by ratios. It doesn't care how big or how small a triangle is, as long as the opposite side is, half the length of the hypotenuse, your angle is always 30 degrees. Try it out, okay? You make a triangle where the opposite side is half the length of the hypotenuse. Guaranteed that the angle down here is 30 degrees, and the angle on top will be 60. All right, so with our calculator, we get that, and that's 6 out of the 7 marks. Your final answer is, well, what does this mean relative to everything? In fact, I think we'd only get 5 out of 7 marks here, because that 23.41 is only relevant to here. We want to figure out this, okay? Where is the green vector pointing up relative to east? You think you figured out how to solve that? We want to add 23 plus that 30 to get the true definition of our theta r. And for that home run, let's consolidate everything together. The resultant displacement is equal to 44 meters east, was at 53 degrees towards the north. And that's it. As for tonight's homework, believe it or not, redo your homework again. There's no point in me asking you any new questions. Just do the same questions as last night, because you should arrive to the same exact answer. And that's it for today. I won't end off right yet. I do want to add one more thing, because many of you guys will get stuck in your homework and you'll be wondering, well, how do I solve this problem here? So that's why I want to give you a heads up. Okay. For example, this question over here. You'll notice that there are 3 vectors involved. And because there are 3 vectors involved, you don't get a right triangle or a scaling triangle. Isosceles? Scaling. You won't get a scaling triangle at the end. All right. You end up getting quadrilateral. Yeah. All right. And cosine law and sine law only work well with triangles through triangulation. So the way how you're going to solve this problem is by breaking up this bigger picture into smaller triangles. I know a lot of students will break it down to this part over here, which I suppose is fine. There's nothing wrong with it that way. But let's just deal with everything systematically. All right. Let's break it up right over here. So in other words, we can deal with this triangle down here by using the cosine law. And after we've solved it, well, the red vector is the solution to these two. So we don't need it anymore. Now we have another triangle, and with that new triangle, we can solve for the green vector. So it would look something kind of like this, where you need to draw out a sketch. You'll have this division line. I always call it delta ds for scaffolding line, because that's all it is. It's a scaffold before you advance on to the next one. So solve for this triangle first. Solve for that scaffold length and direction. After you solve for that, use that in solving for the next triangle. Coolios? As good checkpoint numbers, I'll just leave this up here on the PowerPoint for your reference. You'll end up getting answers like this. Your scaffold length would be that number there. There's the corresponding angles. And if you're careful enough, you'll get to the same resultant answer as in the previous night's homework. Good luck. Oh, just to point out, I do have a tutorial on, I think, this question here or the next one after. I think it's this question here. All right, there's a tutorial on it as well, and it's a good half an hour long. Have fun watching it.